Welcome everyone to SKYLAB's inaugural webinar. I'm your host, David Zeller. The title of today's webinar is Promises, Possibilities, and Problems of Remote Sensing. This webinar arose from discussions with our customers who have repeatedly told us they would like to present new methods and technologies to their company internally. So today we're offering a general overview of how remote sensing works, what results can be obtained, and what you can do with the results. Our experts will explore the possibilities and limitations of remote sensing and AI to optimize and digitize forest management. Today's webinar is aimed at both those who have never had anything to do with remote sensing or are already working with aerial image analysis. Now, first, some notes on housekeeping. Make sure your second Zoom window is set large enough to the presentation slides. So expand it if it's small at this point. If you have questions during the presentation, please write them in the chat function of Zoom, and our presenters will address them following the presentation during the Q&A session. The presentation will go for approximately 45 minutes, and the event will be recorded for later viewing, and you will receive the link. Now I'd like to introduce our first presenter, Simon Mondry. Simon has been with SKYLAB since the company's founding 6 years ago. He has a master's degree in geomatic engineering and is product manager at SKYLAB. He's responsible for photogrammetry, quality assessment, and methodology development. Simon will present recommended data collection methods. Welcome, Simon.
Hi, welcome to our webinar.
And Simon, okay, now I'd like to introduce Rebecca. We'll start with Rebecca Carty-Strange. She's our lead project manager, and she excels at handling complex projects simultaneously. She has many years of managing forest projects around the world under her belt. She's knowledgeable about different sensors and data sources, from high-resolution drone and plane to satellite data. In short, she knows what it takes to successfully manage a remote sensing forestry project. She will share her practical experiences and insights from her many years of experience. Welcome, Rebecca.
Hello to everybody. Thank you, David, for the introduction. And thank you to all of you for taking the time to join us today. I'm going to be talking about the possibilities offered by remote sensing, specifically in the forestry industry, but also where the limitations of the technology currently lie. So what can and cannot be done yet with sufficient accuracy and reliability. And I hope you'll all find it interesting. The good thing about a webinar as opposed to a live conference is that if you want to have a little snooze in the background, the presenter has no idea and won't take offense. The other thing is that if somebody can hear running water, I have a very powerful microphone and a fish tank in the background. It's not that I'm in my bathroom, as you can see. Okay, so I'm just going to explain briefly what we mean by remote sensing. And then my colleague Simon will present a section on data collection, which is really the crucial part of this whole process, because you can only get good quality images, only get good quality results if, of course, you have good quality images in the first place. Then, of course, the part which probably most of you will be interested in is what results can be obtained, with what accuracy, and how can that information be of real practical benefit to the forester in the field? I'm going to talk about 2D image analysis, 3D modeling, and then monitoring of forest change with satellite imagery. Okay, so right, what is remote sensing? So remote sensing is the acquisition of information about the physical characteristics of an area by measurement from a distance. Regarding data sources, the most suitable data source for each remote sensing task obviously depends entirely on the output that you require and the results that you're looking to get. So as you can imagine, the further you move away from the ground in terms of the height at which you're capturing imagery, so from copter drones through fixed wing drones to light aircraft, and then finally up to satellites, the higher you go, the lower the resolution of the images becomes, and consequently, the less detail you have in every picture. So mostly when we talk about resolution, we're talking about spatial resolution. And spatial resolution is the physical dimensions of an area that represent one pixel in an image. So the smaller the pixel size, the higher the resolution, and the more detailed the image. When we talk about temporal resolution, that means the time and frequency of data collection. So for drones and aircraft, that obviously depends only on the availability of the pilot and the machine, and of course, suitable weather conditions. But for satellites, that depends on the frequency with which data is collected over a certain area. And of course, things like cloud cover and other kinds of atmospheric disturbance. Talking about spectral resolution is basically where on the electromagnetic spectrum a sensor captures data. So red, green, and blue, or spectral data, is your standard color photo imagery, which is used for orthophotos, tree counting, 3D modeling, things like that. And then multispectral, which my colleague Simon will talk a little more about shortly, which gives you additional information that you can't always see with the naked eye. So that's kind of helpful for analyzing species distribution and health status. So this is just an overview of the basic process. Firstly, you select your most suitable data source, capture the images, and then the raw images are processed by companies like us. That's what we do here at SKYLAB, with whatever tools are most suitable for the job. So that could be machine learning algorithms, it could be AI, or spectral analysis, 3D modeling. And then, of course, come the results that you get out of that. So the information and the fancy maps that can be used by the foresters on the ground. And now I will hand over to my colleague Simon for the section on data collection.
Yeah, thank you very much for that introduction. And I want to talk about data collection. So before you go into the field, you have to make sure what do you want to map and what's the appropriate data source you want to use. So there are a couple of different sensors, from drones, planes, satellite, and also what method are you going to use, photogrammetry or LiDAR? And do you want to have RGB or multispectral? So that's the main point, or the first point you have to talk about or think about is what do I want to map and what's the right sensor for that? And when you have your right sensor, then make sure that you are able to fly. So, for example, get your flight authorizations and height limits for the drones. If you're planning on flying with a drone, is the weather right? Is it cloudy or not? And of course, if you decide on mapping large areas with satellites, then it should be cloud free, and you have to know when is the right time of getting the satellite images. And to get you a quick introduction into photogrammetry, I just want to show you like small slides and get you the basic informations of photogrammetry. I don't want to go too much into detail, but just so you can have it in your back of your mind, what's the most important things to consider when you fly with a drone or an airplane. So basically you have an object point on the object surface, and this object point is displayed in here 2 images. And it's on different location of these images. And you can connect these lines, and then you get a 3D point. And of course, it's not just one 3D point you get out of these images. You get multiple 3D points, as you can see here with the blue dot. So you get many informations just by taking images, and you can do 3D modeling. But to have these information, you need overlap. And in photogrammetry, we're talking about front and side overlap. And you see it here. A recommended overlap would be 60% side overlap and 80% front overlap. So with that information, we get many 3D points, and we can create orthophotos. On the right-hand side, you can see that the footprint of an image depends, of course, on the flight height, but also on the sensor. So you can see here displaying a DJI Mavic Pro 2. at 120 meter in altitude, which has a ground sampling distance of 2.8 centimeters. The footprint of that image is approximately 150 times 100 meters. So you can cover large areas with a drone, but of course you have to consider the overlap. But why do we need an orthophoto? So an orthophoto is a creation of 100 or hundreds of images stitched together and in high resolution. So on the left-hand side, you can see one image, and you can see on the bottom that you have many distortions. So that's the central perspective. In an orthophoto, you have a parallel perspective, and therefore it's map-like, as we use from Google Maps or satellite imagery. So it's from above, and you can map this area. And before we move on, I want to ask a question. So do you work already with drones in your company? Do you work with multiple drones in the company? Do you have just one drone? Maybe not. Maybe you have just one drone, but not working with orthophotos, or you have no drone and but maybe thinking about a drone, or you don't really consider a drone for planning on doing so. All right, so from what I can see is that about 50% of the listeners are actually having a drone, one or multiple drones, and the other half doesn't. So actually 30% are not planning on having a drone in their company in the future, and 20% are thinking about to have a drone. So maybe this webinar leads to a change, and also maybe the ones who have already a drone are learning new things you can do with the drone. So speaking of drones, you have different kinds of drones. You have copter drones and fixed wing drones, and of course, you have to think about what you want to map, what kind of area you want to map. And speaking of copter drones, they have quadcopters or 6 rotors, but you can depend the speed of the flight really easily, but it has no lift. So it's very inefficient because the rotors have to spin all the time. So you get a flight time of approximately 30 minutes, but you can just cover 50 hectares with that, approximately 50 hectares. It depends on your flight height. If you want to map more, you have to change the batteries. That's all not a problem. But of course, if the areas are getting larger and larger, it's not really convenient. The pros, however, are it's quite inexpensive, and it's really easy to fly. It's ready to fly out of the box. You don't really need so much experience to fly that. And it's really, really portable. So you can just put it in your backpack, go out in the field and start mapping. We are always recommending the Mavic Pro 2, or now we have also a Mavic, or there's also a Mavic Pro 3 with really good camera setups. So this camera is amazing for mapping. And also the DJI Phantom 4 Pro 2 is really good in the camera, and these are our top choices in the copter drone market. Of course, you also can think about the next level, and there the DJI Matrice 300 with a Sony RX1 or Zenmuse P1 camera is also really good. It's a really high quality camera, but you have to consider, for example, in Europe, you cannot fly higher than 120 meters without any permission. So you get a really good ground sampling distance, and most of the times it's not really necessary. With the Sony RX1 or Zenmuse P1, you can fly up to 200, 300 meters. And these cameras, or the Sony RX1, can also fit into fixed wing drones. And you can see, you can cover much more area, you can fly longer, but it's way more expensive than copter drones, and you need an experienced pilot for that. So it's not that easy to fly. And of course, it's heavier, it's bulkier. You need a real suitcase for that because it's just larger. So our top choices here are the Trinity F90 Plus. You can even fit 2 cameras in that, and it's vertical takeoff and landing. So you don't really need a large runway to start the drones. And you can get like a RGB camera and a multispectral camera in that. The Wingtra One is also really good drone, and you can fit the Sony RX1 in there, but just 1 camera at a time. So these are our top choices. Speaking of flight planning, so we always recommend doing flight mission planning apps, for example, like Drone Deploy or Pix4D Capture. Even DJI has a ground station app where you can do flight planning, and it's really easy. It's really handy to fly, for example, with a Mavic Pro 2. So you just have to get in your mission plan, drag your area, or even load in a shapefile. And with that, you just have to press the button, fly, and then the drone will automatically take off, returns as soon as the battery is empty. You change the battery and continues with the flight plan. So that's really easy. But of course, if you want to map larger areas, you have to consider a lightweight aircraft. So more than 1,000 hectares could be beneficial for light craft aircraft, because the costs are actually quite low the larger your area is. And it has a really high resolution camera. And with that, you get a ground sampling distance of 10 to 20 centimeters. And this could also be, if you want to map for your forest, this could be enough, or there should be enough also for 3D modeling. But that's all photogrammetry. There's also a different method I want to talk about, that's LiDAR. So with LiDAR, LiDAR is an active sensor. So you send out a laser pulse, and this returns on multiple levels. So it returns on the canopy, it returns on the ground, and also in between, as you can see on the left-hand side. These are the returns of the signal. So with that, you get an active sensor measuring directly the height of the trees. And with that, you can do 3D modeling quite easily. This is also done with drones, but we are not, it's just changing the technology. So we get more and more LiDAR sensors on drone, but it's still quite expensive and you cannot cover so much area. So when you want to work with 3D models in forestry, you basically need to have a surface model and a terrain model. So the surface model is just the points on the surface. You can get this from photogrammetry or LiDAR. The terrain model is a little bit more complex because not every point on the ground can be seen from photogrammetry, but from LiDAR it can, because it penetrates the vegetation. Here, there's an example you can see on the right-hand side. It's quite a dense forest, and this was done with photogrammetry via drone. So you can see on the bottom many ground points, and if the terrain is not really steep, you can get a tree height model or a normalized digital surface model. When Becky changed the slide, you also know how this is done. So you just have to have the surface model and subtract it by the digital terrain model. And with that, you get a tree height model. So on the right-hand side, you can see everything which is blue is the ground. And the color of red and yellow shows you or displays you the height of the forest. And you can see that there are changes you cannot see on the orthophotos. So this is real good information that you're getting in your forest and really detailed. So what's the pros and cons of LiDAR versus photogrammetry? So LiDAR is really good in dense forest and in steep terrain because it penetrates the forest or the vegetation, and you get ground points as well as surface points. But you get a lower resolution of points because the airplane is flying at a quite high speed, and you just get 4 to 12 points per square meter. This is enough to 3D model, but photogrammetry has a much higher point density. You have no color information in LiDAR, and it's very expensive. With photogrammetry, you get many points per square meter, and it's even more accurate. Because of these many points, you get so much information of the tip of the tree that you actually get better results, more accurate results in tree height. We've proven that in 3,500 hectares in Australia, and with ground plots and ground measurements. And we were really surprised about that. And it was a really game changer, because photogrammetry is 50 to 60% cheaper than LiDAR. So the only limitation is that you have limitations in steep terrain and dense canopy in photogrammetry. But if you have already a terrain model from the federal states, then you have to have. I want to talk about satellite imagery, because if you want to map really large areas, satellites will be efficient. So you can map hundreds of acres, of hectares, have quite a low resolution with up to 30 centimeters. But of course, you have to pay for these 30 centimeters resolution, but you can also get like 10 meter resolution, which is for free, for example, from Sentinel. So the cost varies there quite a lot. So with the satellite imagery, you can also we can also speak about multispectral. There are multispectral sensors also for drones or airplanes, but you can just cover a small area, and as soon as the light conditions are changing, multispectral is quite challenging to do. So with satellites, we cover huge areas at the same time, and here you can see the typical plant reflectance of multispectral data. So on the left-hand side, we can see the visible light, and the reflection, of course, in green of healthy and stressed plants has a peak, but the peak is much more in the red edge or in the near infrared band. So with that, we can create NDVI maps, vitality maps, and look at the forests, vitality. So here you can see an NDVI map of a forest. The red color represents ground or really low NDVI value, and the green color represents a very high NDVI color. So the greener it is, the more vital is the forest. And you can see here gaps in the forest. You can see really dense forest, and with that, you can see if your forest is healthy or not, even from satellite imagery. All right, and then I'm handing over to Becky again.
Thanks very much indeed for that, Simon. That's brilliant. Okay, so now we're going to move on to the results. So what useful information can you get out of all this as foresters? So the results can broadly be divided into three categories: 2D analysis of image data from drones or planes for things like seedling survival monitoring, tree counting, weed mapping, and vitality analyses. 2D analysis using multispectral satellite data for things like monitoring harvesting progress, damage assessment following fires or storms, or regular monitoring of the health of a forest area over time. And lastly, 3D modeling, which again is done using drone or plane data to get inventory information such as tree heights and timber volume. Now, I just at this point wanted to ask you guys a question. Do you have any experience of working with aerial data already? So no, none at all. B, just a little bit, or C, we use it frequently. So if Alex can put up the question on the screen with the interactive voting. Thank you. I'm kind of interested in how many people sitting here today are kind of skeptical about this whole thing and thinking, you know, what are they going to say that's interesting? Or people who genuinely kind of are already using it a little bit and want to find out the full range of possibilities. Oh, wow. Okay. So no, none at all is only 14% of you. And in fact, there's an exact then split with between 43% using it just a little bit and 43% using it frequently. So that's actually really interesting, more than I thought, really. Okay, so moving on then. Currently, the most popular product here at SKYLAB seems to be the seedling survival monitoring using machine learning algorithms and AI. And it's probably so popular right now because it's an analysis process that can be highly automated, meaning that it's very quick and accurate. So the first product that you get from your raw image data is this ortho mosaic that Simon described earlier. This is obviously based on drone data. It gives you just a comprehensive overview of the whole area. So you can obviously see locations of paths, roads, and everything else, but actually you can even see, you can even get a first initial overview of the performance of your plantation by seeing maybe areas of poorer or weaker density. Now, the main question that most foresters have after planting up a new stand is how many seedlings have survived and how many have failed and where are they failing? And normally the way that you do this, of course, is you go into the plantation, you set out terrestrial sampling plots and you count the seedlings in each of those terrestrial sampling plots, and then you extrapolate that over the whole stand area. And of course, that may or may not be representative of the actual situation in your stand, because you may miss areas of significant planting failure or even really good growth as well. And so what AI aims to do, and what it does, is count all the seedlings in the stand, every single one. But training data is crucially important to this process. So I'm just going to give you a little bit of an insight here. This was a stand that we analyzed in Australia back in 2020 with an early version of our AI. And just like any kid who needs to learn, who needs to be fed with information to learn, the models work the same way. So the more information we feed them with, the more accurate they become at detecting seedlings. So this was in March 2020, which a couple of years ago, a little lifetime in AI. And as you can see here, actually, what happened is that the AI has detected some seedlings successfully, but it's missed others. And it has also detected some things that are weeds and not seedlings at all. So then, after a few months of training and putting millions, literally tens of millions of seedlings into the model to give it that information, we reran the same data set of just a few months later, and it was able to detect every single seedling correctly. So it just shows you that training really does matter. It's really crucial. And I'm just going to show you a few snapshots from projects around the world to show you what they look like and what accuracies you can expect to get. So this is obviously like an ideal project. The ground is really clean, the seedlings are visible, and they're planted in nice straight rows. So in projects like that, you would expect to get 97, 98% accuracy in your counting. Another similar example, this is pine seedlings at 6 months in Chile. Again, nice straight rows, nice clean ground, and the accuracy there was about 98%. This is the same kind of conditions, but the seedlings are only 30 days old. That's a eucalyptus in Brazil, so they're really tiny. But because the conditions are so nice and the rows are so straight, we still got about 95% accuracy in that case as well. But unfortunately, not all stands look like that. Some look like this. And it stands like these where that training data is so important. So seedling detection is based on recognition of color and shape of the seedlings and also the planting patterns. So in a case like this, we would first say, well, do you have any cleaner stands where bit less vegetation with the same types of seedlings that we can tell our algorithm exactly what it needs to look for? And then we would train it like that and then apply it to these harder stands, and the algorithm would still be able to detect the seedlings even in these harder circumstances. And the accuracy obviously is a bit lower, but I think the stand was about 90%. And again, a slightly similar one is this, because the seedlings are really quite small and the color is so similar to the vegetation in which it sits. And in this case as well, this is the Northwest USA. There's a completely random planting pattern, so you have no indication as to whether it's supposed to be a seedling or not. And of course, this is really the question, and where I think the major advantage of this technology comes in is that you may have 100% accuracy when you do it terrestrially in your sampling plot, but that maybe only covers, say, 1 to 3% of the total plantation. So in that case, where our standard accuracy is 95%, but let's say even 90%, that 90 to 95% is covering 100% of the plantation. So you still get the complete picture. And the results of the seedling counts can be put into grid cell maps like this that show the number of seedlings per hectare that are surviving in each grid cell. And of course, those grid cells are customizable. This is just another view of that. So this is, it really clearly shows the variability across the stand and any problem hotspots and good survival hotspots, of course, and that can help you to prioritize and guide your plant replanting operations. And also, of course, this is all georeferenced, so you just have these maps which you can hand directly to contractors or replanters, and they know exactly where to go. And also understanding the growth dynamics like this across your stand helps you then to prepare future sites for planting. Now, of course, what happens is once you detect the seedlings and remove all the seedlings from the equation, what you're left with is weed or competing vegetation, and that can also be mapped. So this is a weed density map that shows you where the weed hotspots are so that you can prioritize your management actions. If you do chemical or mechanical weed removal, you know exactly where that's necessary and where it's not. And of course, rather than blanket spraying large areas, you can really target that management. And then of course you reduce your costs and crucially your environmental impact if you're chemical spraying, for example. Measuring the crown diameter is something else that we do as a way of measuring the relative vitality across the stand, because of course at this point the seedlings are not competing for space. So generally speaking, the crown diameter is a very good indication of the vitality of those seedlings. And a lot of our customers have actually reported finding a good correlation between crown diameter and height. And that's what the results of that look like as a kind of grid cell map again. So you can see across the stand the variation in vitality and growth dynamics. While we've been counting seedlings, other products, if you like, have arisen from that. So customers have said, yes, thanks for that information, really great, but can you also do this? And in this case, stump counting was one of them. And the other one that's proven particularly popular is this, counting the number of the harvest residues that have been left behind after harvesting. And we can actually identify the trunks, measure their length and their width. And of course, that way you can calculate the volume of merchantable timber that's been left on the ground. Now, we've looked at all the lovely things that can be done. Where are the limitations of this? So as I mentioned, the more challenging the conditions, the more training data you need to feed and teach the algorithm to accurately identify the seedlings. Although the model does improve with each data set. So seedlings are detected by analyzing a color, shape, and planting pattern, as I explained. So if you have tiny seedlings in very weedy conditions with a random planting pattern, then of course that can be particularly difficult. You do need very high resolution data for this. And by high resolution, I mean 1 to 3 centimeters. So that's the ground sampling distance. And basically, the smaller the seedling, of course, the lower you need to fly to get that same resolution. So seedlings of less than about 10 centimeters in diameter are what we would consider very small. And you can see them if you fly really low, but then that low flight height that you need, that kind of 30, 40 meters, 50 meters, may make it not so economically viable to do that kind of analysis. The other limitation is that we have to train one model per species. So if you have stands with more than 2 or 3 species, that's actually really difficult to analyze. At least it's not difficult to analyze, it's difficult to analyze cost effectively right now. And of course, the accuracy drops as well. So just moving on to adult trees now, this is basically based on the same principle. Counting of adult trees. And this is just one example of this. The accuracy of this, actually, we counted 3,500 hectares of eucalyptus plantations in Australia, and we counted 2,694,214 plus or minus 10. That was the accuracy. I mean, those were kind of perfect conditions, if you like, but that just shows how precise it can be. And again, once you've counted, you get these nice grid cell maps, which show the stocking density per hectare. And this is obviously really useful information before, prior to thinning, post thinning, pre-harvesting. And in this particular case, this is a new plantation in New Zealand for due diligence. They wanted to buy it and they wanted to know what was really there. And while you are counting trees, you can also assess the vitality with the normal RGB color imagery. So here the dead trees are highlighted by the red dots, and the yellow ones show trees with discolored crown tips. So they are clearly stressed because they're brown at the tip, but of course you can't always see that from the ground. And on the right, of course, is the grid cell map, which just shows you gives you an overview over the entire stand where the problem areas are. And last in this section, I'm just going to touch on species mapping. So species mapping can be done by drone or plane using either RGB or multispectral data. And you can create these nice kind of species distribution maps. But this can be done accurately with 2 species, max 3. So limitations of this kind of mature tree analysis. So as you can imagine from the air, you can only count the trees if you can identify them individually. So it's not possible in stands where the crowns overlap. So like most broad-leaved species are not suitable for this kind of analysis. It can be done reliably on almost all conifers, as well as poplar and eucalyptus. We have seen some difficulties in more mature pine stands, like after about 25 years of age, where the tips tend to, the crowns tend to kind of split out a bit and overlap. But having said that, we have also done a lot of projects where the trees are much more mature and it's been fine. It just depends very much on the individual stands. And as I said, stands with more than 2 or 3 species are very difficult to analyze with any reasonable level of accuracy. Okay, so hope you're all still awake and with me, moving on to the section on 3D modeling. And what you can see here in this picture is the measurement of individual tree heights. And this is the tree height model. And it's I want to talk a little bit about this because it's an incredibly powerful tool that immediately shows you the growth variations across the stand. I mean, even in this example of a homogeneous monospecies, even-aged plantation, you can see that the ortho photo at the top there, you can obviously see the gaps and the roads, but what you don't see is the growth variation within the stand. And that bottom tree height model there, where the red trees are the highest ones and the pale sort of greeny yellow are very low, you can see that actually there is a lot of growth variation within the stand. And again, if we put that into a nice grid cell, what that helps you to do, of course, is optimize any kind of terrestrial sampling that you want to do. So you can make sure that you really are including all of those areas of poor and good growth in your sampling, terrestrial sampling design. So this kind of tree height measurements, they can be done with younger trees or larger seedlings, but there's an accuracy of about plus or minus 20 centimeters on this on a kind of average stand. So that accuracy of plus or minus 20 centimeters does, of course, become a much larger uncertainty figure when you're measuring trees of 2 meters as opposed to trees of 20 meters, for example. And in this section, the last part is volume modeling. So volume modeling can be done accurately, but it is a more complicated and customized process. sorry, just one sec there. It does also require some terrestrial sampling information, crucially, because of course, the dBH of a tree cannot be measured from the air, as you can imagine. But based on the information from the tree height model, those terrestrial sampling plots can, of course, be significantly optimized and reduced. And this kind of analysis lends itself much better, in fact, to application on larger scales. So this is just one example of a 7,000 hectare pine plantation in Argentina, where we did a complete inventory and valuation within only 6 weeks, with a tree height model, obviously, to analyze the growth and get a more representative terrestrial sample design, tree count, and also some seedling survival monitoring as well there, and also looking at areas where the plantation is failing and where maybe natural forest is encroaching. So that's all the great things that can be done with 3D modeling, but what are the limitations? As Simon talked about before, we have difficulty creating a good digital terrain model in areas of a very dense forest where there's also sloping terrain underneath with photogrammetry, because you need those ground points. You need to be able to see the ground points from the air. LiDAR can achieve this, as Simon mentioned, but it is much more expensive. Tree height accuracy on younger trees below 1.5 meters there's a much larger uncertainty. It's difficult to inventorize complex forest structures, so like more than 2 species in the same stand or any kind of broadleaf species in the mix. It's uneconomical to do this over small areas, particularly in complex forests, because there's a lot of effort involved. It's not really yet automated, and there's very little payback because, of course, we can't charge a fortune. So it's better to have at least several hundred hectares before you go into this kind of volume modeling, full forest inventory. But having said that, the tree height model can be done easily and accurately and cheaply in any kind of plantations that are a bit more homogeneous and coniferous and on slightly flatter terrain. Okay, so moving on to the last section of the webinar, which is, there we are, satellite data collection. So finally, I'm going to talk about monitoring forest change with satellite imagery. And you can clearly see here the change that's happened on an annual basis from 2016 to 2020. And unfortunately, it's a pretty sad example because, of course, you see lots of negative change in the forest, lots of dying areas, but very little positive change. This is, you can use satellite imagery to assess a weed situation before you want to plant up an area. So that, again, helps you to prepare the site with any chemical or mechanical weed removal efforts. Vitality mapping is probably the most popular use for this. So this is about regular automatic monitoring of forest health and locating and quantifying areas of damage by drought, disease, pests, etc. And this is obviously done on a broader scale, but it helps you really to identify hotspots for taking then more targeted action. And this, over time, it gives you a better understanding of your forests. So particularly now we've got problems with climate change, you know, which species are faring better in which areas under which conditions over time. So this was an analysis that we did in Australia, over 500 hectares of pine forest. We first of all detected dead and discolored trees by drone data, so very high resolution data. But then we had a look at it also with satellite imagery, and actually it came up, it highlighted the same hotspots. So what that means is that you could, in many cases, do a kind of first level health monitoring assessment by satellite, and then send drones to more accurately map the problem areas and detect individual infected trees. Often, so harvest monitoring, often larger forest management companies will have several stands being harvested in different locations at different times. And what this does is give a really good overview of what exactly is being harvested, where and when. And that can be very precisely quantified, either on a monthly or a quarterly basis. So illegal logging, this is an example in Romania where actually there were hundreds of hectares being logged without the knowledge of the authorities. So using satellite imagery in a situation like that can locate and exactly quantify the areas that are being illegally logged. Storm damage, obviously this gives a quick and comprehensive overview following any kind of storms or fires. And actually what was interesting about this particular project, which we didn't expect, was that we were able to differentiate the different types of damage as well. So areas where all the trees had lost their leaves, but they were still standing and would probably recover. And areas where the trees had been completely ripped out of the ground and were just lying uprooted. And species distribution. So this obviously can be done with multispectral satellite imagery. We would need reference data for that, to calibrate. So either like an approximate kind of species map from the forest managers, or either identifying individual groups of kind of reference trees on the ground. But the feasibility and accuracy of this really depends a lot on species that you want to look at, the health of the species, the density, season, and also geographic location. And it's important to point out that the results will become less reliable once you have more than 3 species in the mix. And the last slide I want to put up for the satellite section, which is kind of very pertinent right now, is carbon transparency. So carbon project, you know, in Uruguay or somewhere like that, I'm paying for the carbon credits, but I've got no idea whether it's actually even there, or whether it's been illegally logged, or how it's faring. So this allows you to see very clearly areas where the plantation is being harvested or illegally logged, for example, here shown in bright red, where it's dying off, which is where that kind of patchy red that you can see, where the forest is thriving and growing, shown by the light green, and areas where there's actually newly planted forest, which shows up as that really nice bright green. But what are the limitations of satellite monitoring? Well, of course, it's much lower resolution than drone or plane data, so therefore it's considerably less accurate. You can't acquire accurate information on an individual tree level. It's more about seeing problem hotspots. And it's not currently possible to do 3D modeling, at least not with any kind of level of accuracy. But of course, that will probably change in the near future. The availability of satellite data is obviously restricted by cloud cover because it's above cloud level. Things like poor light, water vapor, or smoke following fires, that all impacts the image quality. And depending on the data source, you may not be able to get good quality images when you actually need them. So in conclusion then, we've come to the end of the webinar. Loads of cool stuff can be done efficiently and accurately, but this technology, generally speaking, works better in kind of more simple plantation type stands, particularly the drone and plane data analysis. There are still significant limitations in more complex stands, so multiple species, steep terrain. But having said all that, AI is improving at a staggering rate, and 6 months is really like a little lifetime in terms of AI. So today's limitations may not be applicable in 1 or 2 years' time. Please use the chat function for any further questions. And thank you very much for joining us. If you're interested in what we can do for you, or have any further questions on anything that we've talked about in this webinar, please contact us at hello@skylabglobal.com. Thank you very much for listening.
Thank you very much, Rebecca, and thank you, Simon, for your presentations. I would also like to apologize for the technical issues at the beginning of the webinar. We will edit this out in a version you will later receive a link to for your later viewing or for sharing with your office colleagues. Now we will begin the Q&A session. The first question was actually a statement from one of our attendees who stated, the best mapping drone is the DJI Phantom 4 RTK. Would you like to comment on this, Simon?
Yeah, sure. And David, you're absolutely right. The DJI Phantom 4 RTK is a really good mapping drone, and I actually missed that in my presentation talking about RTK. So quickly describe what RTK is or does is basically you get a really good georeferencing. So when you map with an RTK system on the drone, you have really precise coordinates, and with that, a really precise map. When you use just a drone without RTK, your accuracy of positioning the orthophoto will be around 3 to 5 meters. So the whole block will be shifted a little bit. But I want to quickly mention one point. So the RTK, or the Phantom 4 RTK drone, has the same camera as the Phantom 4 Pro 2 without RTK. So it's the same camera system in there, and why we experienced good quality with the Mavic Pro 2 is that they have the same 1-inch sensor, but they have a different lens. So they actually, the Phantom 4 has a wide angle lens, or it's more wide angle than the Mavic has. So it's 84 degrees opening of that lens, and the Mavic has just 77 degrees opening. So with that, we get less distortions in the image. And the Mavic Pro has a more color mode, so it has a 10-bit sensor, which also gives you more color information. So that's why we always recommend the Mavic Pro 2 and the DJI Phantom 4 RTK or not. Maybe to consider, there's also from third-party companies an RTK system for a Mavic Pro 2. So you can set it up on the Mavic Pro 2 and get also the RTK accuracy.
Thanks, Simon. Here we have another question. How long does the analysis of seedling counting take? Would you like to answer this, Simon, as well?
Yeah, sure. So we are setting up right now the SKYLAB cloud. So with that, results can quickly shared really fast to the customer. So you upload your images on our web page, and then you can process them there and get a result within a couple of hours, the orthophoto and the seedling count. So that will be done really fast. We're actually launching that at the 1st of February. So because you're an attendee of this webinar, you will also get a mail for that to access the SKYLAB cloud.
Here's another question from David. If we have an experience in assessing wind blow, would you like to address that, Rebecca?
Yeah, so I think maybe he posted that question before I showed the slide on storm damage. Is that so? Because obviously, yes, we do. And as I said in that slide, we were actually surprised by how well the differences in certain types of damage could be analyzed. We didn't necessarily expect to see that kind of level of detail. We applied 2 different indices to try to see that more clearly. So yes, we do, and yes, it can be done.
That was similar to a question from Alexander, who asked if we had experience using satellite data, which we also, I think you covered that just after he had posted that question.
Yeah, exactly. And he made, in fact, exactly the point that I made, that about using satellite data to get a first overview of problem areas in your forest area, and then going to those problem areas to acquire more detailed data. And he pointed that out, and then sent a message saying, okay, I was too fast, because we touched on that. Yes. But that's exactly right. Yeah.
Here's another question. Are you offering trainings in using digital results from SKYLAB? Simon, would you like to address that?
Sorry, can you repeat that question?
If we're offering trainings in using digital results from SKYLAB.
Yeah, sure. We are always really in really close contact to our customers, and if the customer is does not know how to open the data, how to work with the data, we are always trying to help the customer get the data, or display the data in a GIS well, and so we're offering training on request, I would say.
Okay, and I see that David also refined his question about wind blow. He was referring to blown stem counting. Does that make sense?
Yeah, I mean, in actual fact, we haven't done that specifically yet. That hasn't been requested of us, but that harvest residue slide shows that we can detect stems that are lying on the ground. We can count them, we can measure them, length and width, and therefore calculate the volume of the timber that's lying on the ground. So the only question would be then, if in a forest where wind blow is limited to certain small areas, maybe how visible those would be from the air, if there are other trees that are leaning over and blocking the vision. But that's the only limitation. If those can be physically seen from the air, then yes, we can count them, and yes, we can measure them. Is that right, Simon? Did you have anything else to add on that?
Nope, that's right.
Okay.
That's the last of the questions that's come through. So I would like to conclude by saying that oh wait, there's one more question from David. He said he's in the north of England and has had damage from Storm Arwen, which had blown bigger areas down. Okay.
Do you have any aerial data of that area, David? Because we could certainly have a look at it and see what that looks like. But I mean, in theory, yes, of course. So I'll tell you what. There's that email address that I put up, hello@skylabglobal.com. If you just write to us on there, then we can start a conversation about this specifically. But we're very happy to look at that. Yeah, that's certainly theoretically possible.
Well, we thank all of the attendees for your questions, and hope that you've enjoyed today's presentations. Also, since this was our first webinar, we had a bit of technical issues at the beginning, but that's something that we will work out. And we look forward to holding future webinars. So please let us know if there are topics that we should consider for future webinars. And also, if you'd like to hear specifically what SKYLAB can do for your company on your forest management projects with our products and services, please get in touch with us. You can reach us at email, which Rebecca just said, hello@skylabglobal.com, or visit our website, skylabglobal.com. Take care, and best wishes from all of us at SKYLAB. Thank you for attending.
Thank you, guys. Bye-bye.
Thank you. Bye-bye.